Hi, I'm Angel Moreno, and this is my EGN6933 final capstone presentation. Machine learning classification of pathogenic versus benign missense variants. My advisor is Dr. Fan. My instructor is Dr. Marti. The project's goal is to classify ClinVar missense variants as pathogenic or benign using protein language model embeddings, while enforcing rigorous leakage controls and reproducible evaluation. The core motivation is practical. Variant interpretation is high impact, but slow and complex, and we need reproducible machine learning support for prioritization. The final scope was refined. Instead of training a new embedding model, I used precomputed ESM2 embeddings provided by Dr. Fan's lab and concentrated on methodological rigor. My three final goals were: first, build a clean, strict label ClinVar missense dataset; second, design leakage-aware splits that generalize to unseen genes; and third, benchmark models with statistical testing rather than raw metric-only claims. This is the final end-to-end system. Starting from ClinVar and lab-provided embeddings, I apply strict label filtering and quality checks, then generate gene disjoint, train, validation, test splits. I train and evaluate logistic regression, random forest, and XGBoost, then run statistical and error analysis. Finally, I package deployment interfaces, a Streamlit app, and a command line scoring tool. The final curated dataset has 5,000 strict label missense variants, with class composition around 36.8% pathogenic and 63.2% benign. DeLong 10s from Dr. Fan's lab embeddings. Each variant is traced by a canonical chromosome, position, reference, and alternate allele. Key and link to precomputed ESM2 embeddings. What they are: large data dictionaries embedding feature datasets, not trained sklearn model objects. First keys include ID, pathogenicity, embedding, etc. So there are input feature artifacts, not random forest classifier pickles. A major design decision was gene disjoint, splitting to reduce leakage from same gene overlap across train and test. I implemented three model families: logistic regression as a linear baseline, random forest as the practical reference model, and XGBoost with Bayesian tuning as for advanced comparison. Evaluation is area under the receiver operating characteristic curve first, with area under the precision recall curve, and error rates as supporting matrix. Most importantly, model comparison is statistically validated using DeLong and paired bootstrap intervals, so performance claims are defensible. Random forest and XGBoost both performed strongly, but XGBoost did not show a statistically meaningful gain. RF achieved ROC 0.9299 and PRC 0.9473, while XGBoost achieved ROC 0.9265 and PRC 0.9437. DeLong p-value was 0.5523, so the ROC difference is not significant. Error overlap was high, with 56 shared misclassifications, suggesting stable hard cases near the boundary rather than random model-specific failures. This slide shows that RF and XGBoost are very close in ROC performance, and the bootstrap deltas cross zero. So there's no statistically meaningful improvement from XGBoost. To strengthen split validity, I performed a two-stage homology audit. Embedding-proxy screening flagged potentially similar cross-split pairs. Then sequence-level checks were run using Smith-Waterman alignment. The flag train test pair KMT2D versus ARID1A was not confirmed under configured thresholds. The final confirmed leakage rate was 0.0, supporting the robustness of the evaluation setup. This visualization shows the train validation test structure in embedding space, and it supports the claim that the split is clean and not leaking information across the sets. I'll now show the deployed interfaces first in Streamlit. I run a single variant prediction and show confidence output. The decision threshold is the cutoff used to turn a model probability into a final label. How it works: the model outputs a probability for the pathogenic class, like 0.73. The threshold decides whether that score is high enough to call the variant pathogenic. Default is usually 0.5, but in the app and the command line interface lets you change it. Why it matters: lower threshold, more variants called pathogenic; higher sensitivity, recall, more false positives; higher threshold, fewer variants called pathogenic, higher particularity, more false negatives. Threshold affects the final label, not the raw score. Second, I'll upload a demo batch file and highlight the score source summary panel, which reports whether values came from known label overrides, DeLong lookup, or deterministic fallback. Third, here I showed the AUROC and bootstrap delta visuals to separate performance from noise, plus the confusion error overlap view to reveal stable hard cases together. These figures make interpretation reproducible because they show not only point metrics but also uncertainty, overlap patterns, and consistency across models. In other words, it explains why the results are trustworthy, not just report a single score. The command line interface for variant pathogenicity scoring. I including a startup compatibility warning check. My model is trained on 2,560 features, and the command line interface loads it by default. I'll switch to CLI scoring to demonstrate the same interface workflow. A variant lookup map is needed. I ensure that the curated dataset shape, its variant ID, are formatted properly so I can make the CLI accept the real life or the real file names without guesswork. The biggest challenges were data curation, consistency, leakage risk, and avoiding overclaiming due to small metric differences. I addressed these by enforcing strict labels and gene disjoint splits, homology follow-up, and statistical testing. A key lesson is that discipline evaluation and reproducibility are often more valuable than adding model complexity. The impact is a trustworthy baseline pipeline for research-driven variant prioritization and a clear foundation for external validation. This confusion matrix shows the shared error structure between RF and XGBoost. Most errors are concentrated near the decision boundary, which suggests the hard cases are biologically ambiguous rather than random failures. For future work, I plan to validate on external cohorts, incorporate structural and functional context features, enhance explainability with methods like shape or line, and assess assemble strategies with established predictors. In summary, this capstone delivers a reproducible, leakage-aware, statistically validated missense classification pipeline with practical deployment interfaces. Thank you for your time. Thank you for the semester, and thank you for helping me shape me for this project. Thank you.